Right. Good afternoon, everyone. Hopefully you see my screen now. My background is on a tropical island, but I am not a tropical island. I'm in London and giving the talk. Yeah. So today I would like to present a very preliminary work on the overlapping style event detection. I particularly discuss about the problem whether we should consider overlapping events as a multi-label or multi-class classification problem. So firstly, I will give a brief introduction about the audio event detection problem and the common problem that we face in this topic, and then I will go in more detail in the proposed approach that we use to solve overlapping event detection afterward, and that will follow by experiment and some conclusion discussion. So for audio event detection, the problem is very simple. Let's say given an audio recording as shown in the screen, and there's many kind of event happening inside, and we try to we would like to detect some event of interest, for example, dog knocking or baby crying or people falling or phone ringing. And by detection those events, we basically need to identify the identity of the event and also localize where the event happening in time. So it's basically detection and localization in time problem. So that would be.
Do you mind to make your slide a full screen?
Sure.
You can use some Control L and then do.
Yeah. Okay. So that the problem would be would not be that complicated if we have only one event happening at this particular time point, right? But in practice, we may have multiple events happening at the same time as well. So I show here a spectrogram of a recording with multiple events happening, and below the spectrogram, there's the indication of event activity. So at the beginning, we have some class matching event, and then after that, we have some mixer event. And later in the recording, we have dog barking happening at the same time to mixer. And after that, we have some somebody falling happening at the same time to mixer and dog barking as well. And if we look at the time frequency signature of those events in the spectrogram, we see that in the region where we have three different events happening here, we have mixer, somebody falling, and dog barking. The time frequency signature look very complicated. So it should be noticed that for audio, it's very different from image very different from image in computer vision, because for audio the signal is transparent, meaning we at the same time can see all the content, frequency content of the three different events in the spectrogram here. And detection these mixtures is actually very challenging for audio event detection. So I show here some statistics on the decay challenge happening last year and this year as well. So for the event detection and localization task, as I show on the left of the slide, beside the number of sources with the orange column corresponding to the single source, where we have only one source, one audio source happening at the time. Then we have also mixtures of two different sources, and in the decay this year we also had a mixture of three different sources as well. Of course, these are synthetic data, and the way that we create the data is very controllable in the sense that we can decide what kind of mixture that we want to create and how many audio sources that we want to allow to happen at the same time. But in practice, there's no limited way that that we can control such a way as in the lab. And then if we look at the detection performance on the right hand side, so we see that for for the audio segment with only one sources, the performance is very good. For example, in the year 2020, the performance in terms of F1 score is nearly 93%.
Hi, Huy.
Then we look at.
Sorry, Huy. It seems that your slide is frozen.
Really? Can you see my cursor moving?
Here you are showing the overlapping audio events, the slides.
Do you see it's moving now?
No, your mouse is not moving.
Okay. Then in that case, I will try to share it again.
Yeah, maybe, yeah.
Can you see it now, Lynn?
Can you move your mouse?
Yeah.
Yeah. Okay. Yeah, it'll work now.
Okay. I will make it full screen again. Hopefully, it won't freeze. Can you see it moving?
Your mouse is not moving. Are you moving your mouse or not?
Yeah, I'm moving it now.
No, I cannot see it move.
How about a slide change?
Yeah, maybe you can switch off the full screen. Maybe
Yeah, I think the full screen is pro.
Yeah.
So can you see the slide moving?
Yes.
Okay. So I'll stay with this then.
Yeah.
Okay. Again, in the right-hand side, we see the performance of event detection. We have the performance on the single sound source, and we also have performance on the case where we have 2 sources and 3 sources as well. And that we can see when we have more than 1 sources, the performance in terms of F1 score drops significantly. And actually, the event mixture that consists of more than 2 audio sources are the main error source in the submission system in the DK challenge. And here, how usually we deal with overlapping mixture in terms of deep learning modeling. So we usually have a single model, and the popular model we usually use is the convolutional recurrent neural network. So what basically the model does is we take one patch of the spectrogram and then we input into the model, and if the patch is only has one single sources, then it's very easy. We can output. We can deal with that with multi-class classification, right? But to able to deal with multiple sources happening at the same time, the way that we deal with it is we consider the classification problem as multi-label classification. And by doing multi-label classification, we allow the model to output multiple event activity happening at the same time. For example, in this case, with a segment of the spectrogram with 2 different sources, here the mixer and the dog barking event happening at the same time, we output the activity for both of them in output of the network. But this way to dealing with overlapping event has some problems as well. Firstly, the model is hard sharing. That means that there's no controllable way. If we don't specify some way to learn the feature for the classes explicitly, then the network will learn some common feature for all the classes. And another problem is when the model, when we think about the model, how it deal with the mixture event, for example, with a patch of the spectrogram around this region. So again, if we don't have a mechanism to split different sources apart, likely the model will learn the features, I mean, in terms of convolutional kernel, to recognize these mixtures specifically. And that will be troublesome because the model will learn to recognize specific mixture in the training data. And if there's some new mixture in the test data, that's likely that the model cannot generalize over them. And that's actually the problem that we call combinatorial explosion. So when we think about the number of different kind of mixture we can create by mixing different event instances together. Here I show a graph showing the accumulating number of mixture type when we have only 10 different event classes. So for example, here with if we consider on possible on possible mixture of two different audio sources, the numbers is around I think here is around 25. And then the more when we allow more events to overlap with each other, it will create more different type of the mixtures. And eventually, with only 10 different classes, and if we allow on possible mixture, then there's more than 1,000 mixture type that we need to recognize. And that's particularly a problem because that would need a lot of training data so that we're able to cover on different type of mixture that possibly happen in the unseen data. And the number of event mixture types is grow exponentially with the number of classes as well. So the graph I show on the right hand side here is the number of on possible type of event mixtures when we have different number of classes in the system. So let's say with 16 different classes, then we have more than 60,000 event type mixture to recognize. And that is a challenging task to deal with recognition of on mixture event type. So so in this work we try to think a bit what can we do better to overcome the combinatorial explosion in terms of event mixture. And when we think about the model actually learn to recognize specific event mixture type, then why won't we just consider the problem as a multi-class classification problem where we consider a type of event mixtures is one class? But if we do that, we also face with the problem of combinatorial explosion again due to the really large number of possible classes. Then we propose a way to decompose the original problem into smaller tasks. So here, let's say that we have Y different category, then we can decompose Y different category into N different groups. Here we consider simply non-overlapping groups. And then the number of classes in one group is actually much smaller than the total number of category that we have. And therefore, the number of possible event mixture in one group is actually much smaller than the number of possible event mixture when we consider all the class together. And therefore, when we break down the original problem into n different smaller tasks, we're able to consider each of the tasks as multi-class classification problem, and we're able to model on possible mixture event type in the model. So I take one example here. Let's say if we have 6 different event category, baby crying, dog barking, cat mewing, footstep, phone ringing, mixer, then one possible way that we can split them into 3 groups is we group baby crying, dog barking into one, and then with these 2 classes on possible event mixture type with baby crying, dog barking, and dog barking happening together, and similarly for cat mewing and footstep, and phone ringing and mixer as well. This is just one particular way that we can decompose the original problem into smaller tasks, but there should be many other ways that we can do decomposition as well. And as long as we able to decompose the original problem into multiple task problem, we can design a network architecture for multitask modeling. So here I show the model architecture that simplifies for only 2 tasks, but we can generalize it for 8 different tasks. So in the middle of the model, we have the backbone, which is a CRNN model. So basically, this is the typical model that we will use for event detection when we have a bidirectional recurrent network M on top, and then we deal with the detection problem as multitask, multi-label problem. But here we treat that CRNN as the backbone, where we want to learn the generic features by the convolutional block in the middle here. And then from the generic feature that we learn by the backbone, we want to refine it, and then we further learn some specific feature for each of the tasks. And here we have the it's so-called attention convolutional block, where we want to learn a mask to mark the generic features from the backbone, and then we further learn some convolutional features specific to the task here. So I show here more detail about the network blocks. So on the right hand side here, the orange one is the convolutional block in the backbone, where we have two convolutional layers. And then on the left hand side here, we have the attention convolutional block, where we want to learn time frequency attention mask and channel attention mask using the feature output by the first convolutional layer in the backbone. And then we use those attention masks to mask the feature outputted by the second convolutional layer of the backbone to extract some specific feature that's relevant to the task. And then after that, we may want to reduce the number, reduce or increase the number of the channel via the one-time-one convolution here, because we want to combine the features at this level of the hierarchy with the reverse output of the reverse block as well. And then after that, we can design another convolutional layer which is used to learn specific feature for the particular task at hand. And here I go a bit more detail about the time frequency attention and the channel attention. So we want to learn this block to learn the time frequency mask, and this block for the channel attention mask. So this is the time frequency mask. Let's say, so from the output of this convolutional layer, we have a 3D tensor, and then we can perform global average pooling and global max pooling. Then we do the pooling along the channel dimension, and then we obtain the feature map with two channels, and we can combine them together with a one-time-one convolutional layer to obtain a single channel, but we reserve the shape in time and frequency. And then we pass it through a sigmoid activation function to obtain the time frequency attention map. For channel attention, we perform global average pooling along the time and frequency direction, and then we obtain a tensor with a spatial dimension of 1, and the remaining dimension is the channel dimension. And then we use the squeeze and excitation mechanism to squeeze the number of channel, and then we excite it to the original number of channel. And then we pass it through the sigma activation function to obtain the attention mask along the frequency direction, along the channel direction. And given that we have the time frequency mask and the channel mask, then we can multiply it with the output of the second convolutional layer here, and then we combine all together to obtain the features which is specific to the task. To a particular task on the left hand side here. So we conduct a some initial experiment on the database that is synthetic for overlapping event detection study. So in this database, we have 16 different event categories, and we mix different event instances. In this case, we have 994 different event instances, and we mix them together to create 100 overlapping mixtures. And then we use 60 recording for training, 20 for validation, and the rest 20 for evaluation. And there are different degrees of overlapping in this data actually. The event can overlap with a degree of 1, 2, 3, 4, 5, 6. And here for the task decomposition, I consider a very simple composition scheme where the event category appear as the list on the left of the table, and then I can decompose it into two tasks by grouping the first A category together and another task for by grouping the rest A category together. Similarly, we can do it for 4 tasks, 8 tasks, and 16 tasks.
Sorry, Huy, we are a little bit running over time.
Okay, I speed up here. So I show here the performance of the detection system when we compare with the multitask, multi-label classification. So we see that when we decompose the system into smaller tasks, we obtain not only the better performance overall, but also we see improvement on different classes as well. And it seems that there are some optimal number of tasks for this particular experiment. And it seems that 4 tasks and 8 tasks seem to be better than 2 tasks and 16 tasks. And if we look at the result with different overlapping degree, the multitask system actually not only perform well when we have single sources, but also perform better than the multi-label system on the case where we have multiple audio sources as well. And we try to visualize the attention mask of the network too. And for different events, for example, here we have the mixture with 4 different events, and I visualize 2 attention masks for 2 type event, alarm and siren and mixer. And we see the attention masks for different event category actually attend to very different region of the input spectrogram. Right. As we wrap up here, we consider on possible mixture of audio event as classes to perform multi-class classification problem, and we decompose the original problem into multiple tasks to able to circumvent the combinatorial explosion. And we design a multitask network architecture for multitask modeling. And the experiments show quite a promising result. But there are something that we can further improve on the future work, like how can we design a optimal multitask decomposition, and whether we can improve the multitask network architecture and the training scheme as well. Right. Thank you for your attention.